Now we come to our first model. We look at the broadcast channel, which COM message capacity. That's the broadcast channel who would just send COM messages to each sender. That means we have only W0. This problem is essentially the same as the discrete memberless channel. So you need just random coding. So we generate to an R0 code words xn of W0. W0 goes from 1 to 2 to the n R0. And we choose each symbol of each of the n times 2 to the n R0 symbols independently using a distribution Px. So both decoders and the encoder get this codebook. So given W0, we just transmit xn of W0, and decoder 1, given y1 to the n, we try to find a W0 tilde such that xn of W0 tilde and y1 to the n is jointly typical concerning x and y1. If there is one or more such index, then choose one and put out the corresponding W0 tilde as W0 head of 1. If there is no such index, then you just put out 1. The same is done by decoder 1, but with y2 to the n, and of course he checks if this is jointly typical concerning x and y2. And this analysis established that one can achieve rates such that R0 is equal to the maximum over all x and then the minimum of the mutual information of x and y1 and x and y2. See, if you have just one channel, then you get exactly the rate of a discrete memberless channel. For the converse, we know that reliable communication requires that NR0 is less or equal than the mutual information of W0 and W0 head of 1. And also you can write here head of 2, it's the same thing. And this is less or equal than the mutual information between x, n, and y1 to the n. This we can write as the sum here of entropies. This we can estimate by this sum here. And with this, we get exactly n times the sum from 1 over n times the mutual information in xi and y1. And so the n times r0 must be less or equal than n times the mutual information between x and y1, the average of x and y1. So the same holds, of course, for y2 here. We can always insert y2 here. So the final step follows, of course, by the concavity, this step here, of the mutual information as a function on the input distribution. And we set now the probability of ABC equal to this for all ABC. And then, of course, what I told you already, sorry, here it's written down, we can do the same for NR2, that it's smaller equal than n times the mutual information of x and y2 average, so that R2, R0 is less or equal than the maximum over x and the minimum over this mutual information. You see, in principle, it's essentially the same as you did in information theory for the discrete memberless channel. That's the reason why I'm going over it so fast. So the rate is the capacity. So we know this is really the capacity because we have proven that we can achieve this. And you can now look at this. You can also individually, of course, take the mutual information between x and y1 and x and y2, and then take the maximum over x for each individual. Then you get the capacity C1 and C2. But if you take the minimum of the maximum, this is in general smaller. So this capacity is in general smaller than the minimum of C1 and C2. Where C1 and C2 are the capacities of the marginal channels here.